You know that feeling when you're trying to learn something new? Like, say, throwing a basketball. You miss a shot, and then the next time you throw, it's just different. Maybe a little wilder. Well, you're not imagining it. Today, we're going to dig into the science behind that exact feeling, how we learn from messing up, and the surprisingly tricky challenge of actually measuring that whole trial and error process.
It really all comes down to this one simple question. We all kind of know that messing up is part of the deal when you're learning, but why? Turns out when we fail at a physical task, our brain totally shifts gears. It's not just about trying again, it's about how we decide to try again. And here's the core observation scientists have zeroed in on. When you succeed at something, your next move is usually pretty similar, right? You try to do exactly what worked before. But after you fail, that's when your movements get way more variable. You're not just repeating the same mistake over and over, you're actively, maybe even subconsciously, changing things up. This isn't just sloppy, it's a strategy. And this strategy has a name: motor exploration. It's this really cool idea that our brain, after getting that nope, that didn't work signal, literally starts exploring the space of what's possible to find what does work. It's searching for a new solution. This exploration is the absolute engine of learning from failure. But how on earth do you measure it accurately?
Yeah, that's where things get really, really tricky. You'd think it's simple, right? Just measure how much the movement changes after a failure. But researchers discovered that trying to quantify this exploration is a genuine puzzle. There are these little ghosts in the data that can completely fool you. In fact, there are two main culprits that get in the way, two major pitfalls that can completely hide the true signal of exploration we're trying to find. And these aren't obvious mistakes. They're subtle biases that can really throw off the results. So let's break them down.
All right, meet our two troublemakers: performance-dependent feedback bias and reference trial contamination. Now, I know they sound super technical, but the concepts are actually pretty straightforward once you see what's happening. Let's tackle them one by one. So first up is the feedback bias. So picture this. On the trials where you succeed, the very feeling of success can create this weird statistical link between the tiny random jitters in our movements, what scientists call motor noise, and what we're trying to measure as exploration. It basically messes with the data, making it look like exploration is happening when it isn't, or maybe even hiding it when it is. It's kind of like the measuring tape changes length depending on what you're measuring.
The second problem is even sneakier. So, to see how much your movement changed, you compare what you just did to what you did right before, right? That before attempt is called the reference trial. But, and here's the kicker, what if that last attempt was also a failure? What if you were already in exploration mode? Well, now you're comparing one exploration trial to another. And you can see the problem, right? You end up totally underestimating how much exploration is really happening because your starting point is already contaminated. So, with these two massive problems getting in the way, how do we get a clean look at what's going on? Well, a group of researchers developed a really clever new tool designed to do just that, to sidestep these issues entirely. It's called the ATTF method. ATT stands for Additional Trial-to-Trial Change, and its whole job, its entire reason for being, is to clean up the data and give us a reliable, trustworthy measurement of how much motor exploration is actually happening after a failure. It's a way to cut through all that statistical noise and see the learning process as it truly is. And the logic behind it is just brilliant. First, it doesn't look at every single trial. It hones in on very specific patterns, like, say, a success followed by two failures in a row. Second, and this is the key move, it changes the reference point. Instead of comparing the second failure to the first one, it compares it all the way back to the last successful trial, a clean, uncontaminated baseline. And then it just uses some math to subtract out the normal background noise, leaving us with a pure signal of exploration. And the best part? This is what's called a model-free approach. That means you don't need some big, complicated theory about how the brain is wired to make it work. It just quantifies exploration based on the simple outcomes. Did you succeed or did you fail? It gives us this really direct measurement of a fundamental learning behavior. Okay, so what's the big deal? We've got this new, more accurate tool. What does it let us see about learning that we couldn't really see clearly before? This is where it all starts to pay off. This chart lays it all out, plain and simple. The old methods used that potentially contaminated reference point. They were prone to underestimating what was going on, and they were affected by that weird feedback bias.
The ATTC method, on the other hand, uses a clean reference point, gives a way more reliable number, and is built from the ground up to get rid of those biases. It's a real step forward. Now, it's not a magic wand. There is a catch. Because the whole method relies on finding those specific little patterns, like success, failure, failure, you need a ton of data to make it work. You have to run a whole lot of trials just to get enough of those sequences for the math to be reliable. So it's a powerful tool for sure, but it is very data hungry. But ultimately, what this all does is bring us back to this really beautiful idea that every single time we fail, we're not just failing. We're engaging in an exploration of possibilities. Our brains and our bodies are actively searching, testing, and trying new pathways to find the one that leads to success. And now we can actually watch that amazing process happen with so much more clarity. And that leaves us with a pretty mind-bending thought. If we get better and better at mapping this complex dance of trial and error, what's next? I mean, could we design training for athletes or musicians or even surgeons that's hyper-efficient, guiding their natural exploration in the absolute best way possible? The ability to clearly see how we learn from our mistakes might just be the key to learning faster than we ever thought possible.